Welcome, ladies and gentlemen, to today's seminar, Circuit Breaker Maintenance Overview, powered by Encounters Conferencing Solutions. Button on the seating chart panel. At this time, I would like to introduce our presenter for today, Jim Sharkey. Thank you, Jim. The floor is yours.
Thank you, Julie. Good afternoon, everyone. My name is Jim Sharkey. I'm with EPRI, and today we are presenting the first of 3 webcast sessions. The 2 remaining sessions will be on the 20th and the 27th of this month. Both are on Monday afternoons. Each session is from 1:30 to 3:30 p.m. Eastern Daylight Savings Time. I doubt seriously that any of these sessions will go past the 2 hours allotted, especially the third session. The third session will be shorter than most. It only covers cubicle maintenance and safety, but we will cover that in the third session. If you are participating in a group session, if you would, please forward the names of those attending to Tanya Holt at the address on the screen there, T-Holt, T-H-O-L-T, at EPRI.com. And the phone number is there on your screen, 704-547-6094. If you are presenting, or if you are listening in as a group and are not logged in to answer the questions, obviously the CEU credits will not be given. Regarding CEU credits, there will be an optional quiz at the end of each session. There will be 10 questions. There will be multiple choice and true or false, and all answers are covered in the slides presented. Again, the test is optional. If you don't want CEU credit and simply want to participate in the quiz, you can do that also. To request credit, contact Tanya Holt and provide your Social Security number. A few webcast preliminaries. All of this material is posted on the internet. Unfortunately, the answers are not posted on the internet, at least not yet. They will be posted shortly after the quiz. This webcast discusses circuit breaker construction, operation, maintenance, and safety, the emphasis being on maintenance. This material was designed for power plant staff with limited knowledge on circuit breakers and circuit breaker maintenance. If you're a veteran circuit breaker overhaul technician, you will likely be familiar with many of these topics. The course was originally designed for managers or other plant staff that are not familiar with circuit breakers or circuit breaker maintenance. The objective of this course is to raise the level of knowledge and understanding of the purpose, construction, and maintenance of circuit breakers. The scope of this course is limited to plant distribution circuit breakers, 15 kV and below. There were a few emails sent out where it mentioned switchyard, but the scope is limited to plant distribution breakers. The higher voltage switchyard breakers are not covered, although many of the topics do apply. An outline of the webcast is on your screen there. Again, 3 sessions. Today, June 13th, we'll be covering 5 parts. Part 1 is circuit breaker basics, and then we'll move on to breaker types and racking operations, primary components of a circuit breaker, optional equipment that can be added to most circuit breakers. We'll discuss programmatic considerations, and that will be the end of today's session. Next Monday afternoon on June 20th, we'll discuss Session 2. We'll enter Session 2, and Session 2 is basically maintenance tasks. We'll cover why we perform maintenance on circuit breakers, what are typical preventative maintenance tasks. We'll cover overhaul, special, optional, or if applicable tasks, and any other special maintenance topics. Session 3 on June the 27th, we'll discuss switchgear and cubicle maintenance and safety considerations. A little bit more about myself. Again, my name is Jim Sharkey with EPRI. I have previous experience as a Westinghouse main generator field engineer. I was also a fossil plant maintenance engineer at Florida Power and Light. And I have 13 years with EPRI-sponsored circuit breaker users groups. My co-presenter here, Mr. Gene Langlois, is from Waukesha Electric. He has 8 years with the U.S. Navy Aviation Support. He also has 15 years experience with hands-on overhauling of circuit breakers and switchgear. He's previously with ABB, Grand Eagle, and is currently with Waukesha Electric. And I think with that, I'm going to hand it over to Gene, and Gene's going to do part 1, circuit breakers, definition, function, and design criteria.
Thank you, Jim. Just before we get started, Jim and I have been working as a team for quite some time, so I'm going to expect him to keep me on track, so you'll probably
Ladies and gentlemen, we are sorry for the inconvenience. Gene, you may proceed. Thanks.
All right. Apologize about that inconvenience, the technical difficulties. I'm not exactly sure where I lost you, so I'm just going to kind of give an overview right from the beginning of where we're at. Again, myself, Gene Langlois, and Jim Sharkey, and I'm going to be counting on him every now and then. He will add his comments as we go along. And as I said, that the information is basic. And, of course, there's an exception to every rule. So we may come across things that aren't unique or in that way. So, first slide we're going to do is we're going to do the definitions. The NEC defines a breaker as a device designed to open and close by non-automatic means and to open the circuit breaker automatically at a predetermined overcurrent without injury to itself when properly applied within its range. And the IEEE Charlie 37100 defines a breaker as a mechanical switching device capable of making, carrying, and breaking current under normal current conditions, and also making and carrying for a specified abnormal circuit condition such as those of short circuit. That's the definition. We'll take a look at the function. Why do we use circuit breakers? Two major reasons we use circuit breakers are fault interruption capabilities and the ability to open and close the circuit. Circuit breakers are part of the overall protection. Some of the main key components in this are the current transformers, the potential transformers, relays, which are typically found in medium voltage switchgear, and overcurrent trip devices, which are normally found in low voltage gear. If an electrical fault occurs in the system, the relay or overcurrent trip device detects a fault and actuates the circuit breaker in the correct order such that it affects the part of the power system is cleared while leaving the rest of the system in service. One of the ways this is looked at is with the electrical protection scheme is accomplished via the use of zones of protection. And here we have a slide that shows the actual zones of protection. We have zone A, we have zone B. They then feed down, and you're going to look over on the left-hand side, and we have an overlapping zones from the 4160 kV bus zone 1 to the motor zone and the diesel generator zone. After the electrical protection scheme is set up, then what's going to happen is you're going to take a look at short circuit and coordination studies. Now the short circuit and coordination studies is with the equipment interrupting or withstand evaluation of the particular equipment. You're going to see down in the left-hand box we actually have the equipment in its working range. The protective device coordination for electrical distribution systems, including all portions of the electrical distribution systems and we have a list of the basic ones. And all studies shall be in accordance with applicable ANSI and IEEE standards. Now, when we look at this particular equipment, it's going to be in its working range. If you look, current increases, you will see that the breaker will come offline as time is high here, as time decreases. If this breaker is seen roughly 50 amps, if you follow the chart up, it will never trip. It's working in its working range. But if we go over to 1,000 amps and we follow it up, it'll cross the line at some point in time. And if we follow that over, roughly 8-9 seconds before the breaker will trip. If whatever protection that is fails to operate, it will continue up and stay in service for roughly 100 seconds before it trips offline. But most likely it would take not only that equipment, but other equipment with it. So in saying that, on the next slide I'd like to take a look at number 4. or the main power. Now, typically the main power circuit breakers may have redundant power sources, so they can be cross-tied or feed the same load from either breaker. And they're rated for the higher amp than each successive breaker downstream is capable of seeing. In this case, you're going to see we have two arrows pointed to the main circuit breakers feeding the line. Switch 1 is closed. We can open that switch and close the S2 switch. And then we can feed the feeder breakers down below from one or the other main power breakers. The next slide, we'll take a look at what feeder breakers. Typical one line for the distribution of the load center breakers. The breakers separate into smaller branches. And you can see that with circuit breaker 1, circuit breaker 2, and circuit breaker 3. Each branch has its own main circuit breaker, and circuit breaker 2 and circuit breaker 3, which feed the load breakers. Now the load breakers, if one of these breakers in the branches trips open, it normally does not affect the other breakers in the branches or the main feed breaker. i.e., if we take a look at circuit breaker 4, 100 amp, if load 1 shorts, circuit breaker 4 will open, protecting circuit breaker 5 through circuit breaker 7, keeping their loads running. If it fails, it will continue upstream, taking circuit breaker 2 and affecting all of the circuit breakers 4 through 7. That pretty much concludes how the zones of protections are set up. Now what we're going to start doing is we're going to start taking a look at the actual, how the breakers are designed. Circuit breaker design criteria. There are 4 major ones: voltage, current, MVA rating, and fault interrupting rating, symmetrical and asymmetrical current. 2 of the main ones, as far as technicians are concerned, that need to be paid attention to are the voltage and current. Normally your MVA ratings and fault interruptions are set up through ANSI and IEEE standards and are pretty generic amongst all breakers. But you'll see later on where voltage and current will matter. And we're going to take a look at those now. Very first we want to take a look at is the voltage. Normally in the U.S., low voltage breakers are considered between 0 and 600 volts. Medium voltage is 600 volts to 15 kV. And then we continue on with high voltage, extremely high, and ultra high. And the basic thing, the greater the spacing between the phases and the phases to ground, the higher the voltage can be. So a lot of voltages depend upon the insulation. The next major one we're going to look at is current. Now again, it says 0 to 600 low voltage class breakers. So again, we're looking at the voltage and as well as, now we're going to adding the current into that. May have self-protection in the range of 15 amps to 5,000 amps. And the maximal allowable continuous current is determined by the amount of copper in the current carrying contact structures, not the protective device. And you also see that in the medium voltage class below. Normally has no self-protection. It is tripped by means of relaying. But it is very important to keep in mind that just because the current rating of the breaker is set at whatever value it's at, the protection could be set at a lower value.
Gene, this is Jim. Just to interject here, what Gene means by self-protection on a low voltage circuit breaker is what we call an overcurrent trip device. It's mounted, it's a part of the breaker, and that's typically only on the low voltage breakers. The medium voltage type breakers, 600 volts to 15 kV, they don't have the overcurrent trip device as an integral part of the breaker. It's typically separate. It's usually either an electromechanical relay or solid state or maybe even a digital. So that's what Gene means by self-protection. Sorry for the interruption, Gene. Go ahead.
Next one we look at is it gets a little more difficult in the understanding of them. We're going to be looking at the VA ratings, or in the top as it's written as the MVA ratings. You have two that we're going to be looking at. The first one is apparent power. Means the production of the voltage and the current measured in units of volt amps and in standard multiples thereof. Now, apparent power is often used in power ratings as it is more closely related to current than effective power. Effective power, true power, is actual power delivered to the system, and it is measured in watts. This is the only expression of true power is effective power. When we start looking at ratings of equipment, voltage and current do not necessarily happen at the same time. So we must speak apparent power. And we have some triangles of that below. And the very bottom one, you're going to look at watts. Now watts are voltage and current happening at the same time. You're going to see the triangular line that goes up, and that's volt amps. And it all has to do with vector relationships. In other words, voltage and current aren't happening at the same time, and how are they affecting each other in relation to vector. The next one we look at is symmetric and asymmetric faults. Simply, a symmetric fault is a balanced fault, which means all three phases see the exact same fault at the exact same time. Asymmetric fault is also known as unbalanced fault, which means that the fault does not affect the three phases equally. Most of the time, it's a single phase that will see the fault. In practice, most faults in a power system are unbalanced. However, asymmetric faults are difficult to analyze. So most of the manufacturers, when they build the breakers, will do asymmetric faults to the breaker, and then through a complete understanding of the symmetric faults, can then basically tell what an asymmetric fault will do to the equipment itself. Here we have a little chart here of an example of what may come from the manufacturer. This one is a Westinghouse DHP breaker, and it tells the nominal voltage that the equipment can be used at. It shows the MVA class and the continuous current frame size. Just an overview of what we just spoke about. Each breaker is designed to protect the equipment. Allow only the affected parts of the circuit to be tripped or opened under operation. If it fails to open or is not used as within its range, it can take out itself or take out the breaker upstream. Or worst case, not open as designed, destroy itself, and possibly take out other equipment with it. All right, moving on, we're going to take a look at some things that look like breakers but are not. And why we use breakers, not contactors, reclosers, switches, and fuses. First thing we're going to look at is a contactor. Unlike contactors, breakers have the ability to open under fault conditions. If a contactor opens even once under greater load than it is rated for, it could fail. And unlike reclosers, breakers will isolate the circuit after a fault has occurred and will not reclose without a manually initiated signal to reclose. Reclosers will close back in under a known fault on the line, and sometimes more than once, after opening from a fault automatically. Unlike fuses, breakers can be reused after a fault conditions have occurred. And unlike switches, breakers are part of the electrical protection scheme. Breakers can be used as switches, but switches cannot be used as breakers. And just as a note, before circuit breakers were invented, these two items, the fuse and the switch, were put in series with one another for most protection of equipment. And that ends Section 1, Part 1, the definition, function, and design criteria. Section 1, Part 2, we're going to take a look at the circuit breaker types and the racking operations. We're going to talk about circuit breaker types. The different types are molded case, manually operated, electrically operated, manually operated, and stored energy breakers. Then we'll be taking a look at the type of mounting. We have fixed breakers and we have draw-out breakers. Very first one, molded case. These breakers provide overcurrent protection using thermal and electromagnetic for tripping devices. Usually small powered applications, sealed or semi-sealed, and could also be used part as an MCC or bucket unit, which may contain, and we have a list of items such as contactors, controllers, starters, switches, and so on. And the last item we have, as newer and stronger types of plastics are available, large breakers being made of them. And we kind of use the word plastics kind of loosely, because it may be plastic or some other type of material. The basic idea is they are typically sealed or semi-sealed. And we'll start looking at power breakers or metal-clad switchgear. The very first one we'll take a look at is the manually operated breaker, closed by physically closing the breaker with the operation handle. Opening the breaker by physically opening or manually, or by electrical actuation of an installed shunt trip device. So even though a manually operated breaker may have electrics associated with it, but most designs typically say it's manually, depending upon how it's closed, not how it's opened. Electrically operated, again, as we just spoke about, is that the breaker can open and close by electrical signal and can be done remotely as well as locally. The closing is an electrical signal may operate a motor to charge the closing springs or operate a closing coil. Both of these are considered electrically operated. And then the opening is about stored energy from the springs charged during the closing process. Later, design breakers may be designed to be operated both electrically and manually, or what are considered EO and MO type breakers. Closing is typically accomplished by stored energy closing springs. And a key note that some breakers may have maintenance handles that appear to be for charging on closing of the breaker, but are not. So it's important to keep that in mind. Last I'm going to take a look at is stored energy. Typically, most people consider stored energy are spring-charged designs, but there are many other designs of stored energy. Several of which we have here are accomplished by pneumatic, hydraulic, and of course, most common is the spring charging. And that picture's not shown. And that's pretty much it as far as the breaker's concerned, the different types. Next we're going to take a look at is the racking operation. First one is a fixed. Breakers are physically bolted to the switchgear. There's no racking device associated with them. The secondary disconnect, control wiring is hardwired in, may not have primary disconnects. If it does have primary disconnects, Most of the time they are bolted to the primary side, and then the secondary side is cabled in. And that pretty much concludes fixed breakers. Now the next major group is racked breakers, or racking type breakers, and that's done with a racking mechanism. And there's different racking mechanisms may be used to rack out a breaker. Hand crank, levering mechanism, electric motor, and hoist. And you can see this particular design has a racking mechanism bolted to the breaker itself. Some are actually associated with the switchgear and not the breaker. Racking operations, the draw breakers typically have 4 positions: connected, test, disconnected, and withdrawn. And we also have a note to take care that the ground clip must mate even before it goes into the disconnect position or test position. And let's take a look at those a little more closely. First one we have is a draw breaker in the connect position. And you'll see in this particular diagram, the primaries, line, and load side are connected, as well as the control power is connected. The next one we'll take a look at is the breaker in the test position. In the test position, you will see that the primary line side and load side are not connected, but the control power is still connected. In this position, you are able to actually operate the breaker open and close and see the indications. But the breaker is not in a position where you can actually do any type of maintenance on it. The next one we're going to take a look at is the disconnect position. Now, in the disconnect position, you will see that the primary line and load sides are not connected, nor is the control power. Now, some designs, you may have to rack the breaker further out of the cubicle. In this particular design, you see that it actually has an umbilical cord that you just unplug. And no racking is required between the disconnect position and the test position. And the last one we have is the withdrawn position. Now, the withdrawn position differs from the disconnect position in that the breaker is not being held into the cubicle. And a term that is normally used is seismically, which most of you nuclear people may understand if you're from a fossil fuel. It means that the breaker, in the case of an earthquake, will not come out of the cubicle. So if it is physically held in the cubicle, it's withdrawn position. Excuse me. If it's in the physically held in the cubicle, it's in the disconnect position. If the breaker can be removed and inserted, it's in the withdrawn position. And then draw breakers have some way of lifting them out of the cubicle, and normally into the frame or some sort of lifting rig. And caution, make sure you let the equipment do the work. Do not pry or pull on the breakers when you're removing them. Or use wires or ropes and slings, because you could cause the breaker to come free from the lifting rig. That would be bad. All right, that pretty much ends Session 1, Part 2, Circuit Breaker Types and Racking Operations. Next thing we're going to take a look at is Part 3, Circuit Breaker Primary Components. And one of the things we're saying is that all breakers have these particular attributes about them. Main current carrying components, arc extinguishing medium, operating mechanism, controls and wiring, interlock, frame, insulator, and nameplate. Very first one we're going to take a look at is the main current carrying components. Obviously, the main current carrying components carry the current from the line side to the load side of the breaker. And you'll see that on number 17. The stationary contact structure usually has springs mounted behind it for pressure when the number 7 moving contact comes up and strikes it. And that's what maintains the pressure between the moving and the stationary contacts. Also, we have 15, which is the bushings. And the bushings provide insulation between the current-carrying parts and normally the frame of the breaker itself. And one of the other notes is the bridge pivot. And this is a point that provides pressure from the bushings and the moving contact structures. And the bridge pivot allows the moving contact structure to strike the stationary contact structure while allowing current to flow. Contacts. The arcing contacts are used to draw the arc up and into the arc extinguisher during the breaker opening operations. Are designed to take the fault and prevent the main contacts from pitting and splatter. Some particular designs have an intermediate arcing contact, and you'll see in this particular breaker, this is a DB50, that they are part of the arcing contact structure. But you also may find that the arc or the intermediate arcing could be part of the main contacts. And if so, they normally have an insulator barrier on each side of the contact to eliminate the possibility of arc over and contact splatter. And both the intermediate arcing and the arcing contact are designed to protect the main contacts, which designed to carry the normal operating current, close last and open first on all designs. Main contacts will always close last and open first. Next, after we looked at the contacts, we're going to look at arc extinguishing mediums. Arc extinguishing mediums have several different types that we'll be looking at. FF6, vacuum, oil, and air magnetic. The very first one we're going to take a look at is FF6 circuit breakers. In the very upper left corner, you'll see that the breaker is in the closed state. In the upper right, only the tip of the arcing contact is touching. And you'll see that point 8 is moving away. That is the moving contact structure. It's actually moving down. And point 6 is the stationary or the fixed arcing contacts. Look to the lower left. The arc as the breaker opens, and you see that as a white line, and it's actually marked A, the arc. The FF6 gas, at that point in time, you'll see arrows. And these arrows are the actually FF6 gas being pushed past the moving contact structure as it moves down. And then, of course, the last one in the lower right is the FF6 blows out the arc. We have an example of an actual FF6 circuit breaker bottle disassembled. And you see the moving contact structure, you see the stationary contacts, you see the main contacts, and you see the arcing contacts. And you only see one arcing contact shown by the purple. If you look at the moving contact structure, inside this white tube is the actual arcing contact. And that's where the gas is being forced past that tip. Oil circuit breakers basically work identical to what we've just talked about, except that in the oil circuit breakers over the FF6 gas, oil is used to extinguish the arc. There's pluses and minuses to each design. Oil circuit breakers have two different types, unlike the FF6. Now, the first design is a single tank, where all three phases of the contacts are submerged in one single tank. That picture is not shown. It's an old design. Newer breakers that use oil are known as low volume, and each phase has its own oil tank, much like the FF6. And as shown, that's an oil breaker, but it could also be an FF6 as well. SF6. Thank you. Sierra Foxtrot 6.
This is Jim Sharkey again. One thing, Gene is going into some details of the inner workings of the SF6 and the vacuum. The key thing to remember here, this is an overview seminar. The key thing to remember is that there's different mediums. There's vacuum, SF6, air magnetic, and oil. For the type breakers that we're discussing here, those are the four possibilities of ways. These are just different means of extinguishing the arc, and that's the whole purpose here. Is when you open a circuit breaker under load, you're trying to break the arc, and you can either use an air magnetic breaker or you can use SF6. Sulfur hexafluoride gas, or vacuum, or oil. So that's the key thing to remember here. Sorry, Gene.
All right, and then the last one we're going to take a look at, the second to the last, is the vacuum breaker. Now, the vacuum bottles are contacts that separate under a vacuum. Now, the vacuum bottles are sealed units. They don't move very far away from one another, and there is no separate arcing and main contacts. They're actual discs, or look like little plates that actually come up and touch one another. And arc suppression is done by the design of the moving from the stationary, with special cutouts in them that cause vortex or tornado, if you will, inside of the vacuum bottle. And that's what actually helps produce the arc quenching ability along with the vacuum. The last design we're going to take a look at, which is pretty much the most common of what we see at low voltage and medium voltage equipment, which is the air magnetic breaker arc chute. The mechanism or means to extinguish an electrical arc when the circuit breaker is opened under normal and fault conditions. The arc chute is used on each phase and is designed to extinguish the arc as the breaker opens. Here we have a blown out example of the arc chute components. And we'll take a look at the nomenclature. Normally helps you pretty much tell what the function of each part does. Now, when the arc chute moves from the closed to the open state, as shown in the yellow, the little turquoise, you'll see that you have a starting of an arc and the arc traveling up into the arc chute. It is used to contain, cool, and direct the arc. And that pretty much concludes all the different types of mediums in which to control and extinguish the arc. Next one we're going to take a look at is the operating mechanism. Now, the operating mechanism is used to open and close the circuit breaker. The operating mechanism of the circuit is a mechanical device that performs trip, close, and spring charging functions. The operating mechanism function must be fast in order to keep the arcing at a minimum during closing. All operating mechanisms can still be broken down into their sub-assemblies. Three of the most common are the trip mechanism. Now, the trip mechanism must be closed to allow the breaker to be closed. If it is not, the trip breaker can interact with interlocks, which allow the breaker to remain trip-free. The closing mechanism, which allows the moving contacts actually to go from the open state to the closed state. and then a charging mechanism if it is installed. And the thing to keep in mind is even though it's an integral part of one unit, they can all be broken down into separate subsections, or that mechanism could be subdivided and looked at separately. Take a look at circuit breaker controls. Electrical and mechanical devices to control the opening and the closing of the circuit breaker. Most, if they're electrically operated, will have a charging motor, push button, control device, which may have the anti-pump, limit switches, and close coil. You have auxiliary switches. You have secondary disconnects, wiring. And we'll be taking a look at the trip coil on the next page. Now the trip coil on most large breakers is used as a shunt trip device to trip the breaker under fault conditions as well as normal conditions. Unlike most smaller breakers, either don't have shunt trips, or if they have shunt trips installed, are used to trip the breaker under non-fault conditions or normal operations. And we have kind of a definition of what a shunt trip device does. It's more of an armature wrapped around a coil that when a magnetic field is applied, it will draw the armature in and trip the breaker. Look at the electrical controls of a breaker. Most contacts for closing a breaker are in series and are known as permissive contacts. Most contacts for opening are in parallel, which you see these set of contacts can all feed, any one of them can feed this trip coil. Interlocks. Interlocks are two basic reasons: protection of the equipment and protection of the operator. And the thing to keep in mind is all safety interlocks that are installed on a breaker must be mechanical for human protection. And three of the most common are interference, trip-free, and racking interlock. An interference angle prevents you from racking the wrong type of current or voltage-rated breaker into a cubicle. In this particular design, we have an angle and we have a pin. And you'll see that when this breaker can be racked in, the angle will clear the pin, letting this interlock allow that particular design breaker into the cubicle. The next one we have is the trip-free, which prevents the breaker contact from moving to the closed state. As the breaker moves from the disconnect, test, or connect, the lever will strike the tripper bar. This particular lever will strike this tripper bar and will prevent the contacts from moving to the closed state. And that's a definition of trip-free, when the contacts never move towards the closed state. The last one we're going to take a look at is a racking interlock, which prevents the breaker from being racked from one position to another. With the breaker closed, the breaker cannot be racked at all. And you'll see our arrow actually points to this piece of metal. As the breaker goes closed, this particular small piece of metal will be pushed out and actually block the racking cam from moving to the side, preventing the breaker from being racked. And that pretty much concludes the basic interlocks. The next one we'll take a look at is the frame or truck assembly. The frame or truck assembly is used to support the other primary components of the circuit breaker. Normally it's made of metal. The insulation. The insulation is used to isolate the three current carrying pads or phases from each other and ground. A key note, it has to be strong enough to support the bushings, links between the jack shaft and the phases. Not only does it have to be an insulator, it has to be strong enough to support nameplate. The nameplate provides valuable information, and we have a list of items. Not all manufacturers will have all this information, and we have some examples. We have IPE, we have a Westinghouse, and we have a GE. Some of the number one things you will find on the tags are the type of breaker, the voltage, and the current. That ends session 1, part 3 of the primary circuit breaker components. Now we're going to be taking a look at part 4, the optional equipment. The options that you may come across in circuit breakers are current transformers, potential transformers, bell alarms, padlock hasp device, auxiliary switches, talk switches, mock switches, keyed interlocks, local open and close push button, fuses, under voltage device, overcurrent trip device, digital relay type overcurrent trip device, and shunt trip devices, which have already been talked about in the last session. The very first thing we're going to take a look at are current transformers. Current transformers basically provide a ratio between the primary current and provide a secondary current in proportional ratio to the primary current. This primary current is then used to feed protective device metering, and in some cases can be used to actually power up the protective devices. PTs work similar to CTs except using voltage. And if we take a look at the upper picture, we'll see this is a medium voltage CT, and it's installed in the switch here. If we take a look at the lower picture, you'll see that we have CTs. Now these CTs are actually installed on the breaker itself. And if you look closely, you'll see we have 2 CTs. One CT is used to monitor the primary current, and another CT is used strictly to power the protective device. Bell alarms. Bell alarms provide a remote signal that the breaker has tripped under fault conditions. They may also provide a mechanical lockout, which will not allow the breaker to reclose without someone physically going down and resetting that particular lockout. So when you look at a bell alarm, you may find that it's called a lockout or a bell alarm, or both. It could be a bell alarm and a lockout, or one or the other. We have lockout, tagout, padlock devices, which are mechanical safety devices that can be used to lock the breaker in a trip-free position or lock the breaker in a connect, test, or disconnect position depending upon the time of breaker. And most present-day circuit breakers provide a provision for installing a lockout hasp. Older design breakers, pre the 70s, may not provide a lockout hasp or a way to install one. Auxiliary switches. There are various switches on a circuit breaker that provide anything from control functions, logic functions, lockouts, lights, and typically, when you look at these, resistance values should be less than 1 ohm. We'll take a closer look at those next week. We have Mach and truck actuators. Now, truck actuators actually stand for truck operated contacts. And what these do, as the breaker is being racked from the test to the connect position, they let the system know that there is a breaker in the connect position and ready for use. The Mach contact, actuated contacts, change state when the breaker opens and closes. So the truck operated contacts or TOC when the breaker is being wrapped. Mock actuated contacts are when the breaker changes state from closed to open and then open to closed.
Gene, this is Jim again. On the truck-operated cell switch, again, that's in forms of control room and the breakers and connected and ready to go. You may be seeing that again later on, so you might want to make a note of that.
Next one to take a look at is keyed interlocks. Now, keyed interlocks can be used to lock the circuit breaker into an open or closed position. This interlock provides operational controls for personal safety and personal safety. And a key note, one of the common manufacturers is Kurt Key. So it's often referred to not as a keyed interlock, but as a Kurt Key. And then on some particular designs, you may come across local open and close push buttons, which allow you to open and close the breaker electrically from a local point on the breaker. And then you also may come across some sort of manual trip button, which is standard on all breakers, and you may come across a manual close actuator, which does not actuate the closing coil, but uses mechanical leverage to actually trip the close latch to close the breaker. Next item you may find on a breaker is fuse. Now the function of a fuse is to interrupt the flow of current at a specified maximum continuous current rating, a maximum interrupting current rating voltage. Some specified time it takes for the interrupting of the current. Now the fuses are faster than breakers. Some newer design breakers may eliminate the use of fused breakers. And you'll see we have a picture of a fused, and you'll also see a little chart that shows the let-through current through a current-limiting fuse. Now, when you get to the maximum fault current, which is a dotted line up above, some breakers may actually trip open in a cycle or more than one cycle. If you take a look at a fuse, you'll see that the fuse is set and it's only a partial cycle. And most of them contain some sort of sandy type silicon that when the material is heated will turn to a form of glass, which prevents the flow of current and also from the voltage from exceeding a specified amount and jumping across the phases of the fuse. Under voltage devices, the devices that detect a drop in voltage normally connected to the incoming side stabs and sense phase-to-phase voltage on two of the three phases. And we have two types. We have instantaneous, which is the Westinghouse on the upper picture. And then we have a time delay, which you can see at a small little dash pot located at the bottom of the undervoltage, which means that this breaker could see below the rated voltage or whatever the undervoltage is set up for it for a specific amount of time without tripping the breaker. Most commonly found on lower voltage breakers on the breaker is overcurrent trip devices. These particular ones, we're going to take a look at three different types. The first one we're going to take a look at is the electromechanical, then the solid state and the digital. Typically of a low voltage circuit breaker, 600 volts or less. This unit is installed in the breaker and is used in series with the trip device. So current flows through the circuit breaker as well as the protection itself. And you can see that in the upper picture, we have these coils. In the lower picture, we have coils. Normally they are referred to as inverse time elements. So the greater the current flow, the faster the breakers will trip offline. And as a key note, that series trip devices may take 5 seconds to reset, unlike solid state, which can reset in 0.05 seconds. Here's another example of an electromechanical trip device unit actually installed on the lower base molding, and some nomenclature, which again pretty much tells you exactly its purpose and function. Solid-state trip devices. Now, solid-state trip devices were a later design after electromechanical, and they provide a lot or many of the same functions as electromechanical. Again, as stated earlier, they can be reset faster and are usually more responsive to the current. They use a magnetic latch and a solid-state box. So we have our CTs, which will feel the current that flows through a shunt, feeds that secondary current up to the solid-state box, which some people refer to as the brain, and that will be preset as to the predetermined value for that particular cubicle which protects that particular load. When it sees above the fault current, it will send a signal from the solid-state box to the mag latch. The mag latch will then fire, tripping the unit. We start looking at digital relays, which are the modern type. You can come up with many different functions that they can do beyond the solid state. The thing to keep in mind is that digital relays are only as good as the programmed and the program language. Let's review. We have primary components, main current carrying components, arc extinguishing mechanism, operating mechanism, control wires, interlocks, frame, truck, assemblies, and insulators.
And Gene, if you would leave it on this slide. Again, this is something else you may be seeing later on, possibly in a quiz or something. So again, primary components of the circuit breaker include main current carrying components, the arc extinguishing mechanism, operating mechanism, control wiring, the interlocks, the frame, truck assembly, and the insulation. I'm going to talk about some programmatic considerations right now. An overview of this final section for today. We're going to cover a little background, the sources of this material, some terminology, and then I'll go into the topical areas of what I call programmatic considerations, or things that you would consider when you're either building a program or you're assessing the effectiveness of a circuit breaker maintenance program, or you're trying to enhance one. First thing would be documentation, tracking and traceability, procedures, maintenance intervals, lubrication practices, receipt inspections, maintaining the skill levels of your technicians, interfacing with your vendor or your original equipment manufacturer, supporting design basis, and overhaul and refurbishment. A couple of references here. Some of this material comes from an EPRI document called Circuit Breaker Programmatic Considerations, published in December of 2000. And for you nukes out there, there is an information notice that is pretty critical. I feel is critical when discussing circuit breaker maintenance programs, and that's information notice 9913. which if you're a nuke, you're well familiar with that. Just a little background. There are circuit breaker activities within the U.S. nuclear power industry. For you fossil guys, just bear with us here a little bit, but it'll give you some insight into how some of this stuff was developed. Prior to 1990, we had no real maintenance guidance on circuit breakers except from the manufacturers themselves in the vendor instruction manuals. In the early 90s, EPRI began developing maintenance guides for most circuit breaker models in the U.S. In the mid-90s, owners groups were formed. We had a little bit of our regulator gaining some interest in circuit breaker activities and what they felt was an increasing trend of failures. In the late 1990s, nuclear plants began in earnest to overhaul their programs as well as their circuit breakers. And in 2000, we issued that document I referred to earlier. Just some terminology. Preventative maintenance, our definition, yours may be different, but our definition is routine preventative maintenance requires minimal or no disassembly and is performed to ensure a circuit breaker is in good operating condition and will operate reliably until the next scheduled maintenance. Routine PM is also used to monitor the condition of the breaker and correct any minor problems or degradations. Definition of overhaul and refurbishment, as we see it, is complete disassembly of the circuit breaker, that is, no two-piece parts together, cleaning of all parts, relubrication as needed, reassembly, and comprehensive testing. Now, some plants have done overhauls and just simply taken out the operating mechanism. As Gene mentioned earlier, the operating mechanism is a single subassembly that you can, on some breakers, can just remove completely. And that is a good strategy that some plants have employed. And then just overhaul the rest of the breaker. That does save time. So, like I said, there may be other definitions out there that may be just as valid, but that's the working definitions we use. Documenting a program. Documentation can address program ownership and implementation responsibilities. It can contain preventative maintenance procedures, also corrective, troubleshooting and root cause procedures, task frequencies and work scheduling. It can address facilities, tools and equipment, also training for not only for the maintenance personnel, but for the operators and engineering staff is just as important. And any technical justifications. Probably one of the most more important aspects of a program documentation is technical justifications of why you're doing the maintenance you do and at what frequencies. Continuing on with documentation, it can also address design basis considerations. For you fossil guys, design basis is kind of a nuclear term. And use of industry experience, procurement of parts and services, post-maintenance testing, receipt inspections, and pre-installation testing. Again, that's a very important one that we've learned about in the nuclear industry. Vendor documentation and interface, and program assessments. First off, tracking and traceability. We learned kind of the hard way in the nuclear industry that just because a breaker has a number on it doesn't mean it's a unique identifier. And a lot of times it is. A breaker may have a serial number, and if it does, that's fine. You can track the maintenance by serial number of the breaker. Now, what you want to be careful of is tracking breakers by their cubicle number. I know in my plant that I worked at a fossil plant, we tracked maintenance by the cubicle. And it is possible in many, or I would say most plants, that operators have the ability to swap out breakers for operational purposes. If they swap a breaker, then you've lost your maintenance record. So a key thing is maintenance should be tracked by serial number or unique identifier. If they don't exist, you should probably create one if you want to properly track your maintenance of each individual circuit breaker. We also learned somewhat the hard way that shop order numbers should not be used, as shop order numbers may not be unique. Moving on to procedures. Preventative maintenance and overhaul practices should consider or include vendor recommendations, and a lot of times, again, those are in the vendor manuals that you get originally. But in addition to that, procedures need to be updated through vendor updates, bulletins, letters, or any other modifications that the vendor may have come out on your circuit breaker. And in addition to that, you should also include your own operating experience from your plant via input from your own technicians. These are the guys that work on your breakers, PM the breakers, so they have the most intimate knowledge of your breakers. Also, your utility. If you have if you're one plant out of many in a utility, which most of y'all probably are, you can gain operating experience or maintenance experience from your other plants. So that should also be included in your preventative maintenance procedures. In addition, if you have a mechanism, a lot of times the fossil industry is limited here, but if you have a mechanism to gain operating experience or maintenance experience from plants outside of your industry or your utility, that would be prudent to do that. If you have significant deviations from your vendor recommendations, for example, if you have your original vendor maintenance manual that came with your circuit breaker, if it gives an overhaul interval of, say, 8 years, and you're significantly deviating from that, it might be wise to document that. There's many reasons for that, but one of the reasons, if you change jobs and the next guy comes in and he's wondering why you're doing something different than 8 years, then he'll just move it back to whatever the manufacturer says, and that lesson learned will be lost. So, bottom line is document significant deviations from your vendor recommendations so that you'll have a record of it. Moving on to maintenance intervals. There are a wide range of factors that you should consider when selecting maintenance intervals. They include environment. Is the environment dirty or clean? What kind of safety significance does the breaker have? For nuclear plants, this is especially critical. If you have a nuclear reactor coolant pump, obviously that's a critical load. You want to make sure that the breaker is well maintained for that load. The impact on plant operations. This applies to just about every plant out there. If a breaker is critical to your plant, you want to make sure that breaker is maintained properly. Also, manufacturer's recommendations, obviously, should be included as a consideration. Your lubricant life expectancy. If you have experience on when your lubricant dries up and the life expectancy of that, you may want to include that. Your own maintenance history and current condition of your circuit breakers. I would emphasize this. A lot of, if you do not know the condition of your breakers, or you know that your breakers have not been maintained in the past, and this this is not uncommon. If you know your breakers have been not maintained or maintained incorrectly in the past, you want to include that in your consideration of the maintenance interval. Also, industry experience, I already mentioned, and of course your plant maintenance philosophy. This is just a graphic that shows a lot of the things that I just went over. Lubricant life expectancy, maintenance history, current condition, operational history, environment, so forth. Maintenance intervals. Maintenance intervals, we feel, should be determined on a plant-by-plant basis. The justification for these intervals, you may want to document these in your plant maintenance programs. And of course, manufacturers typically provide guidance on task intervals. Some of them may or may not, usually it's preventative maintenance intervals, and they may or may not discuss overhaul. By their own admission, the guidance from these manufacturers represents their best generalized advice and may include conservative or liberal assumptions about circuit breakers' environment, lubrication, previous maintenance, and operational history. The manufacturers that supply your breakers are supplying them not only to your industry, but to many other industries. It may be an electric plant, it may be a petrochemical plant, it may be an oil platform. They have no clue as to the environment and the type of application where you're going to use your breakers. So they have to make assumptions about maintenance intervals. Some manufacturers have recognized this, and they've encouraged their plant personnel to identify their own plant-specific consideration, modify maintenance intervals as needed. And this slide is again, just to support that. We pulled two direct quotes, one from an ABB maintenance and surveillance document, and another from a Westinghouse instruction bulletin. I won't read these, but again, it just supports the position that we've taken. Moving on to lubrication practices. Obviously, use-only lubricants approved for use on the circuit breaker. There's a reason why the manufacturer selected that lubricant or that grease. And if possible, identify lubrication points. This is a little bit more difficult to obtain. Usually the manufacturers don't provide this type of information, but if that's possible to do, then that's a good thing. Avoid over-lubrication. Gene Langlois is going to emphasize this in the next session, next Monday, but I'll go ahead and emphasize it here. It's probably one of the most common mistakes made on both PM and overhaul is over-lubrication. Avoid commingling or mixing of lubricants. Lubricants may be incompatible. There's synthetic and natural lubricants. There's all kind of different lubricants out there, and they don't all work together. They may be incompatible. Verify lubricant shelf life. For storage and handling, you got to avoid contamination. You got to store it at the proper temperature and so forth. There's also application methods, special tools. Some of these special tools for lubricating a breaker either during a PM or overhaul, some are even sold by the manufacturer themselves because the manufacturer has developed them for maintaining the breakers in their own shops. Receipt inspections. This is something that we've learned in the nuclear industry, and I'm going to emphasize this point. Receipt inspection should be performed whenever maintenance work is performed by any service provider, whether they be a third party or the original equipment manufacturer. Receipt inspections are needed after a breaker is sent to offsite or overhaul for corrective maintenance. It may consist of a routine preventative maintenance task or a subset of these tasks. This type of inspection ensures the breaker is fully functional before installation and can operate until the next maintenance outage. It's a good practice to perform these shortly after the breaker is received on site. If you ship your breakers out for overhaul or maybe corrective maintenance, as soon as they get back to site, you should check them over. As a side note, this also helps facilitate resolution of any contract issues if you should run into any. Also, if you're lucky enough to have spares and you store spares for an extended time, maybe in a storage facility, before you pull that breaker out and stick it into a plant, it's also good practice to do a PM, either a full-blown PM or just check the breaker out. Maintaining technician skill levels. I won't go into any detail, but this is obviously important. There are many ways to do this, and there's no single correct method. It'll depend on your plant's training program and a variety of factors. How much staff you have, what kind of resources, the number of circuit breakers you need to PM, and so forth. But we couldn't complete this presentation without talking about maintaining the technician skill levels. The training, they should have some type of periodic training, either refresher or maybe even detailed if you're doing an overhaul program in-house. And the program owner or system engineer responsible for tracking procedures and maintenance intervals and so forth should also have some type of training. Vendor interface. It's a good practice we found to periodically contact the manufacturer. Obviously, for you fossil guys, there's no real requirement to do this. For the nukes, there are some requirements, but it's just a good thing to do to do this periodically. And if you find that they have technical updates, bulletins, whatever type of information, you can use that to upgrade your procedures. Supporting design basis, again, this is primarily for the nukes, but obviously you need to ensure that throughout the life of the plant that electrical coordination and protection is maintained. Ensure your overcurrent trip device settings agree with your coordination studies. If you have fast bus transfers you need to worry about, then that's something you need to consider. And also, if you have reduced control voltage conditions, will your circuit breaker operate? Those are some things you need to consider. Moving on to overhaul and refurbishment. If performed by a manufacturer or service provider, know what you are paying for. Know what the manufacturer is going to do to your circuit breaker. Ask him if you can review their own procedures, or a lot of times the manufacturer will give you specifications or a summary of what they're going to do to your breaker. If you can, specify what is to be included in the overhaul and possibly post-maintenance testing. If you can, send a representative, use witness points or hold points. And the main thing I do want to stress is, if you're sending your breaker out to the manufacturer, and you say, well, they're the ones that made the breaker, manufactured the breaker, and they're the experts on it. Don't assume that the work is going to be done correctly. In other words, just because you send it to the OEM, that doesn't mean it's going to work correctly. Anyone that's working on a breaker, be it third party, your own plant technicians, or a manufacturer, you should check the work and perform some type of post-maintenance testing or checking. Now, most of the fossil plants out there typically, I would say, don't have in-house plant overhaul, or excuse me, circuit breaker overhaul programs. If you do, and I'm sure there are exceptions to this, but if you do in-house overhauls, in other words, your own utility and utility personnel overhaul circuit breakers, some of the considerations are you need long-term management support. Obviously, that always helps. If you're going to have an overhaul program, in-depth initial training is going to be almost a requirement. This may last anywhere from 1 to 3 weeks. You got to maintain their skill levels after that by either refresher training or periodic overhauls. Facilities, you got to make sure the facilities are adequate, proper tooling, and so forth. Also parts are a big part of an overhaul. And you can still, on top of that, have assistance or oversight from the manufacturer. Also, parts a lot of times are modified, upgraded, they're enhancements. You have to stay on top of that as well, or have the manufacturer help you with that. Oops, skipped a slide there. Talking about trending, predictive and condition-based maintenance, EPRI's got a lot of questions over this through the years. Breaker maintenance has been and continues to be primarily time-based. It's just because of the nature of these older circuit breakers that we have in a lot of the plants. EPRI has investigated condition-based maintenance practices, but again, they're not easily applied to circuit breakers. Lubrication analysis, vibration, you know, some of these have been investigated, but they're not really all that effective. Thermography, we have had some success with thermography. Obviously, like motor control centers, panel boards, that type of thing. Thermography is very effective in defining and locating hot spots. You can do reduced control voltage testing. It's typically not trended. It's a pass-fail test, but it does provide some information on the operation of the open and closed coils and their interaction with their respective enclosed components. It does not provide an overall condition of the circuit breaker. There are many components of the circuit breaker that you have to look at. Some plants are using ultrasonics, a very small number, but they are using ultrasonics primarily for safety reasons. Ultrasonics can detect some arcing. There is the timing test. It determines the response time during opening or closing operation of the circuit breaker. It includes the coil response time, the mechanical response time, in other words, how long mechanically the breaker takes to open or close, and time for the contacts to physically separate or close. The timing test is a fairly easy test to perform. The travel test, it can be done, timing test can be done during a PM. A lot of times it is, but the travel test is a much more involved test. It requires much more setup, and it provides additional information for the extra work you have to do. It'll provide over travel and under travel of the arcing contacts, and this is in the form of an actual printout. It'll show you rebound when the arcing contacts rebound. The velocity by which when the breaker opens and closes, the moving contact assembly, there's a velocity associated with when it opens and when it closes, how fast it's going, the distance it travels, and the penetration. You can get all of this information from a travel test. Very worthwhile test, especially either before or after, especially after you've done an overhaul. You want to make sure that circuit breaker operates properly. Let's see, moving on to, continuing on with trending and predictive condition-based maintenance. On certain circuit breaker models, there are mechanical and or electrical tests that can be quite valuable in determining the condition of the operating mechanism or electrical components. Mechanical tests I'm talking about are trip shaft torque and trip shaft force. Now, Gene is going to cover these next week in a lot more detail, but basically these are just mechanical tests that, again, it's breaker specific. It may not be able to be performed on your breakers, but a lot of breakers you can do this. Certain mechanical tests that will tell you somewhat the condition of your mechanism. And of course, contact resistance. For example, a Westinghouse DHP breaker, it has a bridge pivot inside the main current carrying components, and you can actually look at that contact resistance, and that will tell you a lot about how the breaker is put together and the condition of that bridge pivot. So the main thing is these are breaker specific, and to really have a good PM, you need to look at your maintenance manuals and understand what's in there and know what you can do on your breakers and how to maintain them. Well, I think that's getting. How are we doing on time here? 3:13. Okay, we're in the Q&A session. Julie, are you there?
Hold on, I'll forget.
I am.
Oh, thank you.
And
I think we can. If I don't believe do we have any questions?
we do have a question in the queue that has come in. How is the maintenance of the circuit breakers typically tracked or maintained? And if you guys do have any questions at this time, please remember that you can ask a question by simply go to the question and answer section of your console, type in your questions to the left of the Ask button, and click the Ask to Submit button.
Okay. Julie, the question was again, how are breakers tracked?
Correct.
Okay, I think I can feel that one, Gene. There's a variety of ways breakers can be tracked. In other words, we're trying to track maintenance here. In other words, when I was talking about unique identifiers, you've got to know what breakers have been PM'd, what have been overhauled, which ones have been overhauled, and so forth. You can take a very simplistic approach, or you can take a complex approach or middle of the road. A simplistic approach would be just a simple Excel spreadsheet. And I know many plants have just done this. A person responsible for breaker maintenance just develops a simple Excel spreadsheet, and he uses that to track which ones have had PMs, the dates, and so forth, and when they're due again. And you can get a little more sophisticated and make a database, sort of like an access database. Maybe your IT department can develop this, or you can get really sophisticated. And there are barcodes that you can put on individual breakers and software programs, and even have Palm Pilots where you can just walk around the plant and do an inventory of breakers, and the software will tell you exactly the location of all your breakers. So you can go simplistic, middle of the road, or very complex.
And one of the things I've also seen is people not using the manufacturer's actual serial numbers, but actually just stencil their own, 1, 2, 3, 4 on up, on the breakers themselves. So rather than tracking it by the serial number, they simply just track it by their own unique identifier for that plant. Hope that answers the question. Is there another one?
I see another one. Is that
It's been on.
Oh, okay, that one. Will this presentation be available? Oh, okay, you've already answered that. I don't see any other questions. I guess we can move on into the quiz. Would that be okay, Julie?
That would be great. Just let us remind our listeners how to go ahead and do the polling questions. Please take a brief moment to, and what we'll do is you'll see a poll that it does appear, and just click on the button that corresponds to your answer.
Should I advance the slide, or how do we do this, Julie?
Yeah.
Ah, there we go. I see the first question there. Should I read it, Julie?
That would be great.
Okay. What are the design criteria for circuit breakers? I would add a comment here. Always choose the best answer. Choose the best answer. Read all the answers and choose which one is the best.
So, what are the design criteria for circuit breakers? Please press red if it's a size, weight, and fault interrupting rating. B, voltage, current, fault interrupting rating, MVA rating. Yellow if it's the manufacturer model number. And green if it's all of the above. Did you want to go ahead and close the polls, or did you want to keep them open for our listeners?
I think
We're going to try and keep them open for just a little bit.
Okay, great. As we are waiting, please remember if you do have any questions in the queue, you may also ask them. Just type in your questions and press the Ask button. Did you want to go on to the next polling question?
Actually, we're going to give the attendees 30 seconds
Okay,
or
great.
a bit more to answer each question. Right now we're at 32. We're still looking at the poll, and once it starts slowing down, we'll move on to the next one.
Okay, great.
Okay?
Next question. The circuit breaker can be used as a switch, but a switch cannot be used as a circuit breaker. A is true, red or blue is false.
And did you want to give them the answer to the last polling, or are we going to do that after the quiz has been done?
We'll give that after. That's the last.
Okay, great.
All right, moving on to the next question. In which racking position is the control power connected? The key point in that control power. Is it the red, connect and disconnect? The blue, test and racked out? The yellow, connect and test? Or D, none of the above? Okay. I think we can move on to the next one. Who's Julie?
Did you want to move on to the next poll?
Julie, I'm sorry. Who's clicking these? You or
I'm not clicking at all. Did you want to go ahead?
I'm sorry.
Oh, no problem.
The primary components of a circuit breaker include A, main current carrying components, mock and talk switches, control device, or B, the nameplate, operating mechanism, and bell alarm, or C, the operating mechanism, the frame, and insulation, or D, controls and wiring, mock and talk switches, and contacts. We'll give you all a few minutes to answer that. Okay. Give you all a few more. Another minute here. Again, choose the best answer. Okay. I think we'll move on. Next question. Insulation on a circuit breaker is used to isolate the phases from each other, A, or B, used to isolate the phases from ground or earth, or C, not a part of the current carrying path, or D, all of the above. Okay, just a few more seconds on this one. All right, we're about to move on here. Okay, let's move on. Next question, what piece part of the circuit breaker informs the control room that a breaker has been racked from the test position to the connected position? Either A, main contacts, B, secondary contacts, C, truck-operated cell switch, or D, keyed interlock. We'll give you all a few minutes to answer that. We'll give y'all some more time. There's still some people that hadn't answered this one yet. Okay, just a few more seconds and we'll move to the next question. Okay, moving on. Next question, a circuit breaker maintenance should be tracked by a unique identifier such as a serial number. True or false? Okay, we'll give you all a few more seconds on this one. like we got most responses on that one. Just a few more seconds. Okay, we'll move on. Next question. What information should you include when developing your plant's circuit breaker maintenance procedure? A, the manufacturer's manuals and any other guidance from the manufacturer, including technical bulletins and letters. B, your plant's experience and past problems encountered at your plant. C, manufacturer's recommendations, operating experience, and input from technician. Or D, your plant and industry's operating experience only. Again, choose the best answer. Just a few people hadn't answered that, so I'll give y'all a little bit more time on this one. Okay, looks like just a few more seconds on that question. Okay, let's move on. Next question. Preventative maintenance intervals should be determined by each individual plant and can vary due to a variety of reasons. True or false? Okay, about to move on to the next question. I think most everybody's answered that one. Okay, let's move on. Well, trying to move. Oh, that's it. That is all of them. Yeah. Oh, let's go back a slide here. That is the end of the quiz. I hope everybody did well. We will review the answers to the test questions, I believe, right now. Julie, is that okay?
That's great.
Okay. Let me pull up another presentation that has the answers in it. Just give me a second. Okay. Question 1. Why do we use circuit breakers? The answer is C, for fault interruption and opening and closing the circuit. Next question. What are the design criteria for circuit breakers? The answer is B, voltage, current, fault interruption rating, or MVA rating. Again, the answer is B. Question 3, a circuit breaker can be used as a switch, but a switch cannot be used as a circuit breaker. The answer is true. That is correct statement. Moving on to question 4. In which racking positions is control power connected? The answer is C, connected and test. Question 5. The primary components of a circuit breaker include, correct answer is C, an operating mechanism, the frame, and insulation. Mock and Tock switches are auxiliary add-on devices. The nameplate, bell alarm is an option. A nameplate usually comes with a breaker, but a bell alarm is an option. And contacts answering D, and of course Mock and Tock switches are contacts are part of the primary current carrying component. So the correct answer is C, operating mechanism, frame, and insulation. Question 6. Insulation on a circuit breaker is all of the above. D, it's used to isolate the phases from each other, from ground, and is not a part of the current carrying path. Obviously, it's insulation. So correct answer is D. Number 7, what piece part of the circuit breaker informs the control room that a breaker has been racked from the test position to the connected position? This is one of those ones I said, hey, you might want to note this. It is a truck-operated cell switch. Answer C. Question 8, circuit breaker maintenance should be tracked by a unique identifier such as a serial number. We went over that in the programmatic considerations. That is true. Question 9, what information should you include when developing your plant's circuit breaker maintenance procedure? This is the one I made sure to caution you. Choose the correct answer. The correct answer is C. Manufacturer recommendations, obviously, your operating experience, and input from your own technicians. Question 10 is true or false. Preventative maintenance intervals should be determined by each individual plant and can vary due to a variety of reasons. That is true. That pretty much concludes the question and answer. We have a few questions. Gene has been reading the question manager here, so I'm going to give it over to Gene now.
I have a few questions that were typed in that I'd like to answer. One of the questions was, what is the specific lubrication recommended for breaker maintenance? It says IE3M Dow Corning. The correct answer is you should follow the manufacturer's recommendation unless you deem that you find a better lubricant. And that is true if you're a fossil fuel. Now, if you're a fossil fuel, if you choose a lubricant that best suits your purpose, i.e. if you're water treatment facility or some sort of chemical facility that you have a problem with certain types of lubricants hardening ahead of time, you may choose to contact a lubricant manufacturer to see what it reacts with. Based upon that, you may choose to use a certain type of lubricant that will not react with the certain types of metals and, as just spoke about, certain types of chemicals at your plant. And if you step away from the manufacturer's lubrication, you should have some justification or reason for it. And at certain commercial and industrial plants, I've seen that done quite often. But keep in mind, do not mix the lubricants from the old ones to the new ones, especially in the primary disconnects. All right, there was also one other question that was asked about the micro-ohm resistance value of medium voltage. And normally, what is seen for a 1200 amp breaker, about 40 microohms. For a 2000 amp breaker, about 30 microohms. And for a 3000 amp, about 20 microohms. But keep in mind that this is based upon a brand new or an overhauled piece of equipment. During preventative maintenance, typically that can be exceeded by 50% of what is documented in the manufacturer's guideline. And we're currently reviewing some of the other questions.
Just to interrupt for just 1 second, we do have a listener stating that they didn't receive question 1. So I don't know if we did go over question 1 on the quiz.
Yeah, we saw those questions too. Actually, there were several people that mentioned they missed question 1. I don't know why that was. There might have been a delay in the PowerPoint, or maybe we just advanced the slides too quickly.
Okay, great.
I think Tanya will address that with y'all. We may, for CEU credit, we may just have to give you answer 1. I'm going to leave that determination up to Tanya.
Great. I just wanted to let you know that.
Yeah, if you missed question 1, just get with Tanya via email, and she'll work out what to do there. There was also one other question. I may be able to respond to this one. Check me out, Gene, if I'm off base here. But the question was, which type and manufacturer of medium voltage breakers has the highest failure rate in the industry? Well, that's a pretty loaded question. That's really difficult to answer. First off, there's not a whole lot of data on such things that's readily available. In the nuclear power industry, we have a little bit more resources to track failures, but I don't think we don't really go out and try to find out who's got the most failures out there. We try to be a little bit impartial. Obviously, we're EPRI. That's kind of a difficult question to ask because, again, when you're looking at data, some of these databases are difficult to interpret, and it's not a clear cut where, hey, this breaker has 800 failures and this other breaker has 400. It's just not that clear cut. So it's very difficult to even ascertain an answer to that question. So whoever asked that, I hope that will serve as an answer.
The only thing I'd like to add to that is specific manufacturers have specific challenges. In other words, that if GE, the same people who engineered one type breaker, typically are involved in engineering the later breakers that come out by that same manufacturer. And they will have specific challenges to that particular line.
And as far as, there's industry databases, and obviously you can say, well, why don't you just go to the manufacturer? Obviously there are problems with that too. Manufacturers, even if they do have databases, they may not tell you they have that, or they may not tell you they track that, because let's be honest, they're just not willing to share that information with the rest of the world. So it's very difficult to ascertain an answer to that question. I don't see any other questions. We appreciate everyone logging into this. We had a pretty good response. We will have the next session on next Monday afternoon. There's 3 sessions total, and you can review this information will be posted on the internet website. If you have any other questions, feel free to email Tanya Holt or myself, Jim Sharkey at EPRI. My email address is jsharkey@epri.com. And can't think of anything else, Gene.
No, sir. Thank you, everyone, for your time.
Thank you.
Thank you, Jim and Jean, and thank you, ladies and gentlemen, for your participation. This does conclude today's seminar. Don't forget to close your browser and disconnect your phone. Thank you and have a great day.